Hello everyone, today we are going to discuss about the inductance of the transmission line. In this lecture, we are going to cover the following topic: the line inductance, flux linkage due to the single current carrying conductor, flux linkage in parallel current carrying conductor. So before we start this topic, we should know the main parameters of the transmission line. So the main parameters of the transmission line are resistance denoted by R, inductance denoted by L, capacitance denoted by C, and G, that is conductance of the transmission line. These are very important parameters of transmission line. It determines whether the voltage regulation of the line will be good or poor. That is, the performance of the transmission line is determined by these parameters. So this is important for the electrical design of the transmission line. In this lecture, we are going to discuss about the very important parameter of the transmission line, that is line inductance. When an alternating current flows through a conductor, a changing flux is set up which links the conductor. Due to this flux linkage, conductor possesses inductance. So mathematically, inductance L is equals to Xi by I, where Xi is the flux linkage and I is the current. So suppose we have a conductor, this is a conductor, and it is carrying a current, alternating current, that is I. Due to this current, a magnetic field will produce around the conductor, and hence there will produce a magnetic flux, and this magnetic flux will link with the conductor, and hence it produce what? Inductance, that is this. So from this diagram we can say that the flux linkage, that is flux linkage phi, is proportional to what? Current I. That implies flux linkage is equals to Li. So we have mathematically proved this equation, which is already written here. And here the Xi flux linkage can be written as Xi is equals to what? N into phi. N into phi, where N is the number of turns and phi is the flux, magnetic flux. Since it is a transmission line, so value of N will be equals to 1. So the psi is nothing but psi will be equals to phi. Now we are going to discuss about the flux linkage due to the single current carrying conductor. As in figure 1.2, we can see that a conductor of length L is carrying a current I and having a radius of R. So total inductance of this conductor will depend upon the flux linkage due to the internal flux and flux linkage due to the external flux. So first we will discuss about the flux linkage due to the internal flux. Now let Ix is the current flowing inside this conductor, due to which internal flux will produce, that is phi, at a distance of x meter from the center of the conductor. And due to this flux, there will be a internal flux linkage. So here we can see that due to the internal current I of x, there will be production of a what? Internal flux at a distance of x from the center of the conductor, and hence we will obtain what? Internal flux linkage of the conductor. Now here the magnetic field intensity, which is denoted by H of x, at a point x meter from the center is given by, at the x meter from the center is given by H of x is equals to I of x divided by 2 of x. Now how we have obtained this? By Ampere's circuital law, the MMF means magnetomotive force around any closed path is equals to the current enclosed by the path, that is net current enclosed by the path. Here the net current enclosed by the path is I of x. In other words, we can say that the closed surface integral of H dl will be equals to I of x. And here H into d of L will be equals to 2 pi of x will be equals to I of x. So by this way we have obtained this equation. Now we are assuming a uniform current density across this conductor. Since the current density is uniform, so we can say that J is equals to I upon A, where J is the current density and I is the total current flowing through the conductor, and A is the area of cross section, which will be equals to I upon pi r square will be equals to I upon pi x square. So from this we will obtain, here it will be I of x by pi x square. So from this we will obtain I of x, total current I of x flowing inside the conductor will be equal to pi x square by pi r square into I. So by substituting the value of I of x in the above equation, we will obtain H of x is equals to x by 2 pi r square into I ampere turn per meter. Now, if mu is the permeability of the conductor, then the flux density at the considered point is given by B of x. Mathematically, flux density is given by B of x equals to mu naught mu r H of x, where mu naught is the vacuum permeability and mu r is the relative permeability. So relative permeability is 1 for non-magnetic material. So we will obtain mu naught, that is mu naught xi divided by 2 pi r square, Weber per meter square. Now the flux d phi through a cylindrical cell of radial thickness d of x and the axial length 1 meter is given by, in this figure, if I zoom it so that I can show you, in this figure, at a distance of x from the center of the conductor, that is d of x, a flux will develop in the closed concentric circle that will be what? D of phi. So this d of phi will be equals to b of x into 1 into d of x is equals to mu naught we have already obtained the b of x value from in the above equation, so we will put this equation here. Then we will get mu naught xi by 2 pi r square d of x. Now d phi, now here d phi, the flux link with the current Ix only. Therefore, the flux linkage per unit length of the conductor is given by d phi d xi is equals to x pi r square by x r square into d phi. So substituting the value of d phi from the above equation, we will obtain mu naught I x cube by 2 pi r की power 4 into d of x Weber turn. Hope you have understand till now. So now the total internal flux linkage from the center of the conductor to the surface will be given by integral of 0 to r mu naught x I cube 2 by 2 pi r की power 4 d of x. Very important, please keep in mind. Now we are going to discuss about the flux linkage due to the external flux at a distance of x meter from the center of the conductor. Now the magnetic field intensity at a distance of x from the center of the conductor is given by h of x is equals to I upon 2 pi x at ampere turn per meter, as we have already discussed while we are deriving for the flux linkage due to the internal flux. Please refer that. Now the flux density B of x we know is mathematically represented as B of x equals to mu naught h of x. So we have substituted the value of h of x, then we will obtain mu naught I by 2 pi x Weber per meter square. Now the flux d phi through the cylindrical shell of radial thickness d of x and the axial length of 1 meter is given by d phi is equals to b of x into 1 into d of x. We are considering here the length as 1 meter is equals to mu naught I by 2 pi x d of x, as this value we have already obtained in the previous equation. So the flux d phi will link all the current in the conductor once and only once. So d phi equals to d xi is equals to mu naught I by 2 pi x d of x Weber turns. So the total flux linkage of the conductor from the surface of the conductor from the surface of the conductor to infinity is given by integral of r to infinity mu naught I by 2 pi x into d of x Weber turn. So the overall flux linkage we can write it as internal flux linkage that we have obtained earlier, and the external flux linkage is equals to mu naught I 8 divided by 8 pi plus integral of r to infinity mu naught I by 2 pi x d of x is equals to mu naught I by 2 pi. We have taken it common, then it is multiplied by 1 by 4 into integral of r to infinity d of x x. So this is the overall flux linkage, which unit is Weber turn per meter length. Now we are going to discuss about the flux linkage in a parallel current carrying conductor. Now here we are assuming a parallel current carrying conductor, that is A, B, C, D, E and F. These are all parallel current carrying conductors. Assuming that the conductor A is carrying a current that is IA. Similarly, conductor B is carrying a current IB, conductor C is carrying a current IC, and so on. So we have to find the total flux linkage in the conductor A. So now the total flux, to calculate the total flux linkage, we have to calculate the flux linkage of the conductor A due to its own current, that is I of A, is given by, as already we have derived in previous slide, mu naught IA by 2 pi 1 by 4 integral r to infinity d of x by x. Now flux linkage with the conductor A due to the current IB, that is nothing but mutual inductance or mutual flux linkage. So when the current IB is flowing through the conductor, then the flux will link with the conductor A, which is given by mu naught IB by 2 pi d1 to infinity d of x by x. This is nothing but it representing the external flux linkage to the conductor A. See, here we have to understand that when conductor is carrying a current IA, for own current the flux linkage will be due to the internal flux, and due to the external flux also. But flux linkage with the conductor due to the current IB will be a external flux linkage to the conductor A. So we have to keep in mind this is nothing but external flux linkage to the conductor A. Similarly, the flux linkage with the conductor A due to its current IC is given by mu naught by IC by 2 pi integral d2 by infinity d of x by x. As this is integral from d2 to infinity, because the distance between the conductor A and C is d2. So d2 to infinity dx by x. So now the total flux linkage with the conductor A is given by, just what we will do, we will sum up these all, that so on. Similarly, the flux linkage will be due to the current ID in the conductor D. Similarly, flux linkage due to the current IE in the conductor E, and the flux linkage due to the current IF in the conductor F, and so on. So by adding this and this and so on, we will obtain the total flux linkage with the conductor A. Thank you so much. Have a nice day.